Hi, my name is Salim Al Rouayheb. I'm from Rutgers University, and today I want to talk about privacy from an angle that is a little bit different than usual. I want to talk about how to be able to turn privacy on and off and on again, and the problems that come with that. And this is a joint work with my collaborators, Carolina Naim, Fang Wei, and Hoon Cho. In this talk, we want to think of privacy as an expensive service or an expensive utility that it would be nice to turn off when not needed and turn it on back again when needed. Maybe a good analogy here is electricity and how one usually turn off the lights when one leaves the office or one leaves home. And our motivation is that irrespective of which privacy formulation or privacy metric one follows or one adopt, typically privacy preserving or private algorithms have higher costs and higher overheads in terms of computations, memory, and delay. And for this reason, we would like to reduce this overhead by turning privacy off when not needed. One common example nowadays would be the private mode in internet browsers. But actually, we're thinking beyond that. It could be any case where a user would not want or would not care about privacy or would care about privacy only in a limited time. For instance, someone who works in a company and using company, say, computers and smartphones, and he wants privacy to be on only when he's not at work, when he's home. Or maybe someone who's using a public Wi-Fi connection, and at that time he would want privacy to be on. But then when he goes back and he uses his own personal connection, he wouldn't mind privacy being off. And what I'm interested in here is the problem that may look very easy at the first sight, which is how to design algorithms that allow privacy to be turned on and off whenever needed. Now, a straightforward solution to this problem would be what we call time sharing, meaning one would have two algorithms, one private to be used when privacy is turned on, and one non-private to be used when privacy is turned off. And one would just jump between these two algorithms or time share between these two algorithms, depending on whether privacy is on and off. Now, unfortunately, this solution is not private or may actually lead to leaking lots of information. And this is because typically the way data is requested and searched and processed is correlated over time. And this would lead to the leakage or lead to compromising privacy. To illustrate this idea, let's take an example of an Uber driver who want to go on a break. And while he is on break, he does not want to reveal his location to the company. So that's why he turns his privacy on. Now, once his break ends, he needs to reveal his location to the company and start picking up passengers. But he cannot just immediately reveal his location and turn privacy off because that would reveal his location while he was on a break. In other words, this is because we don't know how to do teletransportation yet. We don't know how to disappear from one place and appear in a totally different place. And this kind of correlation is the challenge here. So this means that one has to be really careful when turning privacy off because this would reveal information about what happened when privacy was on. So probably this driver would have to drive a little bit further and then turn his privacy off and start picking up passenger. And this is exactly what's the problem that we want to look at, is that how correlation how to deal with correlation when turning privacy off. And correlation is everywhere and not just peculiar to location. For instance, it appears in application where users browse information online. For instance, user watching videos, they just don't sample videos and watch videos on YouTube independently. So a user wouldn't jump just from music videos to, say, politics, to fashion, to sports independently. So human beings tend to have some correlation based on their taste and how they consume information. Also, this correlation is also appears in graphs such as social graphs. So the way information about one user will leak information about his friends, and also it appears in genomic application where, for instance, there is lots of correlation in DNA sequences. So even if one would like to hide certain part of the DNA because it may reveal some personal traits or some predisposition to diseases, one has to be very careful because that part that is need to be hidden is correlated with what comes before and what comes after. Now, to be able to mathematically quantify this interaction or trade-off between correlation and privacy and understand how algorithm could be constructed that allow privacy to be turned on and off, let's look at this problem from an information retrieval perspective or framework. So we consider the scenario where a user is trying to retrieve information from a server. Think of it as a user trying to watch YouTube videos, for instance. So the server has n information sources that we call A, B, C. You can think of these as the YouTube channel. And every YouTube channel or every information source produces a new message of length L at each time t. Now at each time t, the user is interested in one of these videos, xt. So xt tells us which source he's interested in at that stage. And now to represent correlation, we resort to the simplest correlation model, which is the Markov chain. So the Markov chain tells us what's the probability of the user wanting a message from a channel C, let's say, given that currently he's at A. So the main idea of Markov chain is that the transition probabilities do not depend on the past, they just depend on the current model. And privacy can be on and off. And basically when privacy is on, what we want to hide, what the user want to hide is XT. So he wants to hide XT from the server when privacy is on. When privacy is off, he doesn't care about hiding XT. And to understand this trade-off between correlation and privacy, we're going to take an extreme measure of privacy. So we want absolutely no information to be leaked to the server when privacy is on. So we represent this by the mutual information. So we want the mutual information between the user query Qt and all his interest xt when the privacy was on to be equal to 0. So here I think there is a typo. So here it should be xt. So Qt is his request, his query to the server at time t, and xbt is the information he's trying to hide when privacy is on. And our goal, we look at schemes that allow us to turn privacy on and off, and also that kind of maximize the download rate. And the rate RT at time t is the size of the message that the user is interested in divided by the download, how much he or she downloads. So for instance, so the best thing is the rate, the maximum rate is when the rate is equal to 1, meaning everything the user downloads is actually what he or she wants. But of course, the rate is gonna be less than 1 because we want to have privacy. So sometimes we may have to download more to confuse the server. But basically, this is the measure that we look at. Now let's try to form a bit of intuition about this problem, and let's focus on a toy example. Let's suppose we have 2 YouTube channels or 2 sources, and the user interest is described by this 2-state Markov chain. So here, for instance, the probability that the user want to go from channel A to channel B is alpha, and from B to A is beta, and so on and so forth. And also let's assume that the privacy was on for all time that are negative, and then privacy is turned off. So the idea is that if we can solve this problem, this is going to give us lots of intuition on how to solve the general problem with more than 2 states and where privacy on and off can be switched at any time. Now, the first thing that one can think of is that let's forget about privacy being on and off, and let's treat privacy as being always on. So if privacy is always on, what can one do? So from the theory of private information retrieval, since there is a single server and we want privacy, perfect privacy in an information theoretic sense, then if you want perfect privacy in this case, you must download both messages, both videos from A and from B. Because if you do anything else, you're gonna leak some information. And in this case, the rate is 1/2. And this is actually optimum from when privacy is on, because this is the best thing we can do, just download both videos. But then when t is larger than 1, we're ignoring the fact that privacy is turned off here. So the rate is not optimal for t is larger than 1. But this is something to start with. Now, the second idea that one can think of is that maybe one can treat privacy, although we turned off privacy at t equal 0, but maybe someone can keep privacy on up to a certain window here, and then actually turn it off. So basically one can keep downloading two videos, both videos from both channels up to a certain time window. This way you kind of decrease the correlation and then start requesting your actual video in the clear. And obviously this works, but then this is not private, because once you start requesting the video you want in the clear, then you're gonna reveal what you wanted before, and there is a correlation between here and what you wanted at t equal to 0. The correlation is definitely less than between t equal to 1 and t equal to 0, but you're still leaking. And it turns out that what we show is that the optimal solution could be interpreted as a probabilistic mix of these two simple schemes. So I thought the best way I can explain the results in this short time is to give you some intuition of how to solve this simple case. So it turns out that once you turn privacy off, the first question is, how should I deal with t equal to 1? So what should I request at t equal to 1? It turns out that the optimal scheme would be the following. If what you want at 1 is different than what you want at 0, if they are different, then just you can request what you want in the clear. And this is the case when alpha plus beta is less than 1. And because if alpha plus beta is equal to 1, then it means that there is a high probability that you keep getting the same message from the same state. Now, if x0 and x1, meaning what you want, are the same, A or BB, then now you have to split between either requesting exactly what you want, which is A, here because you want A, or you download both of them. And here too, if you want at t equal to 1, you want the same thing at t equal to 2, which is B. Either you choose B with a certain probability or A, or both of them, A and B with another probability. Now, if you do the calculation and the probability, you're going to see then in this case that the query Q1 is actually statistically independent of X0. So you're leaking 0 information. Now for t larger than 1, what you do is exactly what you did at t equal to 1 until you hit the case when you download either A or B individually. And once you do this, meaning you revealed what you want, then you stop hiding what you want. From now on, you just request what you want in the clear. Now, if in the previous case, you requested both A and B, then you implement the same scheme again. So in some sense, this is kind of a window with a geometric, with a probabilistic size. The probabilistic size that depend on alpha, beta, and also on the states of what the user wanted. So in that sense, you're actually implementing a probabilistic version of these two schemes. You're actually downloading both or not, and you keep doing this at a certain window, and then you start requesting things in the clear. So, and you can prove that this actually is the optimal rate, and it leaks 0 information. And here I have the rate, so you can see here. So you can check the details in our ISIT paper, and now it's a transaction paper, transaction and information theory. So for t less than 0, the rate is 1/2 because you have to download both because privacy is on. And then you can see that the optimal rate is gonna increase as time increases because the correlation decreases, so until it hits 1. And then you can see that the rate also decreases as alpha plus beta decreases. That is because as alpha plus beta decreases, the correlation is increasing. Now, for more than 2 sources, it turns out that the problem is a little bit more complicated. We don't know the optimal rate, download rate, but we have upper bound and lower bound. The main idea is that scheme that I showed you is based on solving an LP program. And then for n larger than 2, then the constraints in the LP program actually blow up exponentially. We have a polynomial time algorithm for solving this LP program, but actually it's not always optimal. Thank you for watching this talk, and feel free to email me if you have any questions, and you can find more information, especially more technical information, in the following publications and the following video talks.